The concept of time travel has captivated humanity for centuries. From the earliest days of human civilization, people have been fascinated by the idea of moving through time, whether to revisit the past or to glimpse the future. This fascination is evident in the myths and legends passed down through generations, where heroes and gods often possess the ability to traverse time. From ancient myths to modern science fiction, the allure of journeying through time remains a persistent theme. Stories of time travel have evolved over the centuries, reflecting our changing understanding of the universe and our place within it. In ancient times, time travel was often depicted as a magical or divine power, while in modern science fiction it is frequently portrayed as a technological achievement. Imagine stepping into a machine, traveling to the past and witnessing historical events firsthand. You could see the construction of the pyramids, the signing of the Declaration of Independence, or the first moon landing. The possibilities are endless, and the idea of experiencing history as it happened is incredibly compelling. Or, picture yourself hurtling into the future to explore the technological marvels yet to come. You might find yourself in a world of flying cars, towering skyscrapers, and advanced artificial intelligence. The future holds countless possibilities, and the idea of seeing what lies ahead is just as exciting as revisiting the past. These ideas have fueled countless stories and sparked our collective imagination. From H.G. Wells' The Time Machine to modern films and TV shows, time travel has been a central theme in many beloved works of fiction. These stories allow us to explore the what-ifs and the might-have-beens, providing a unique lens through which to view our own lives and the world around us. But could time travel ever move beyond the realm of fiction and become a scientific reality? Scientists and physicists have long pondered this question, exploring the theoretical possibilities of time travel through the lens of modern science. Concepts like wormholes, black holes, and the theory of relativity offer tantalizing hints that time travel might one day be possible. The desire to unravel the mysteries of time is deeply ingrained in our nature. We are constantly seeking to understand the world around us, and time is one of the most fundamental aspects of our existence. By studying time, we hope to unlock the secrets of the universe and gain a deeper understanding of our place within it. We are constantly moving forward, leaving behind moments that are gone forever. Each second that passes is a moment we can never get back, and this relentless march of time shapes our lives in profound ways. Our memories, our experiences, and our actions are all influenced by the passage of time. The past shapes our present, and our present actions influence the future. Every decision we make has the potential to impact the course of our lives and the lives of those around us. By understanding the flow of time, we can make more informed choices and strive to create a better future for ourselves and for future generations. But what if we could break free from this linear progression and explore time in all its dimensions? The idea of moving through time as easily as we move through space is a tantalizing one, and it challenges our very understanding of reality. Whether through the pages of a book, the frames of a film, or the equations of a scientist, the dream of time travel continues to inspire and captivate us, pushing the boundaries of our imagination and our understanding of the universe. To understand the possibilities of time travel, we must first turn to the groundbreaking work of Albert Einstein. His theory of relativity, published in the early 20th century, revolutionized our understanding of space and time. Einstein proposed that space and time are not separate entities but rather interwoven aspects of a single fabric spacetime. Imagine a stretched-out sheet representing spacetime. Objects with mass, like stars and planets, create depressions in this fabric, much like a bowling ball placed on a trampoline. These depressions represent gravity, the force that pulls objects toward one another. Einstein showed that gravity is not a force acting at a distance but rather a curvature in spacetime itself. One of the most intriguing implications of Einstein's theory is the concept of time dilation. This concept, which stems from his theory of relativity, fundamentally changes our understanding of time and space. It suggests that time is not a constant, unchanging entity but rather a flexible dimension that can be stretched or compressed depending on various factors. Time, it turns out, is not absolute but rather relative to the observer's frame of reference. This means that two observers moving at different speeds or in different gravitational fields can experience time differently. For instance, an astronaut traveling at high speeds in space would perceive time differently than someone standing still on Earth. Time dilation means that time can pass at different rates for observers who are moving at different speeds relative to each other. This phenomenon has been confirmed through various experiments, such as those involving precise atomic clocks placed on fast-moving aircraft. The clocks on the aircraft showed a slight difference in time compared to those on the ground, proving that time indeed flows differently depending on speed. The faster an object moves, the slower time passes for that object compared to a stationary observer. This effect is not noticeable at everyday speeds, but becomes significant at speeds approaching that of light. For example, if you were to travel in a spaceship at 90% of the speed of light, time would pass much slower for you than for someone on Earth. This effect becomes more pronounced as an object approaches the speed of light, which is the ultimate speed limit in the universe. According to Einstein's theory, nothing can travel faster than light. As an object gets closer to this speed, the time dilation effect becomes more extreme, theoretically allowing for significant differences in the passage of time. Theoretically, if a spaceship could travel at a significant fraction of the speed of light, time would slow down for the astronauts on board relative to people on Earth. This means that while the astronauts might experience only a few years of travel, decades or even centuries could pass on Earth. This concept opens up fascinating possibilities for space travel and the future of humanity. Upon returning from their journey, the astronauts would have aged less than their counterparts back home. This scenario, often referred to as the twin paradox, illustrates the profound implications of time dilation. One twin traveling at high speeds in space would return younger than the twin who stayed on Earth, having experienced time more slowly. In essence, they would have traveled into the future. This idea, while seemingly like science fiction, is grounded in the very real and tested principles of physics. It challenges our conventional understanding of time and opens up new avenues for exploring the universe. As we continue to push the boundaries of space travel, who knows what other fascinating discoveries await us in the vast expanse of the cosmos. Section 5. The Multiverse, a tapestry of infinite possibilities. One possible solution to the grandfather paradox and other paradoxes of time travel lies in the concept of the multiverse. The multiverse theory suggests that our universe is just one of an infinite number of parallel universes, each with its own unique timeline and set of physical laws. If the multiverse theory holds true, then traveling to the past might not alter our own timeline, but instead transport the traveler to a parallel universe with a similar but distinct history. In this scenario, any changes made in the past would create a new branch of reality, leaving the traveler's original timeline intact.